Just to summarize, yesterday we learned about accomplishments from different communities, in particular astronomy, multi-messenger astrophysics, and high-energy physics, about what they are doing to address computational grand challenges. Can you see this slide correctly, or is it overlapped with images?
It looks good.
No, it's fine.
It's good? Okay, great. And this was a great exercise just to get a broad perspective of activities happening not just in the US, but also in Europe. Now, on day 2, what we actually want to do is to hear from now different people that are leading projects related to harnessing the data revolution, and outside of this program, related to other domains like geosciences, and also in the context of industry engagements. So we are going to start the day with a panel where we summarize what the people organizing this conference are up to in terms of innovative applications of AI and computing for astronomy and physics. We are also going to hear from Patrick Brady, who's joining us representing the SCiMMA project. And if you attended Mario's presentation yesterday, you have an idea about the type of effort that they are also leading. It is also a community building effort. And then we also have Raf Margutti, who is a leading figure in the LSST collaboration. And then after that, we are going to have presentations from people that are very active in the application of extreme scale computing and machine learning in geosciences. And then we will have also a presentation from the director of data science at Phillips 66 about how they want to actually engage with us to cross-pollinate the expertise we are developing as part of these programs to advance the activities that they have from an industry point of view. And then we are going to end the day with a presentation from a different flavor of the HDR program, which is tripods. This is about scientists just developing new tools in terms of foundational AI, innovative computing, etc. So this is the order of the day. And now I'm going to pass this to Dan Katz, who's going to be moderating the panel. So it's all yours, Dan.
So I'm Dan Katz from the University of Illinois. This panel is going to be, as Eliu was saying before, about different HDR and HDR-like projects that are going on, with the goal of kind of understanding what's going on in those projects and thinking a little bit about how the projects potentially could work together, if that makes sense. So we will start with 12-minute, roughly, talks from each of the panelists, and then we should have about half an hour for discussion at the end. And so I think we start with Phil Harris from MIT.
Hi, yeah, so I'll just go through the slides that we have. Okay, so this is just going to talk about our HDR, which is Advancing Science with Accelerated Machine Learning. And kind of the vision and mission for this project was to bring together a few different ideas. So we wanted to have some science drivers. So we have the challenge in high energy physics and gravitational wave astrophysics of running, let's say, machine learning at scale. So in high energy physics, the problem here is that we have data rates that are exceptionally large, right? So our raw data rate is a petabyte per second. And then our, let's say, our saved data rate is about a petabyte per day. And basically between the petabyte per second and petabyte per day, we have various tiers of computing. And in all of these tiers at the moment, there's some use of machine learning, but it's limited. And it's limited basically to use on CPUs. And so basically our challenge here is to integrate machine learning into GPUs or FPGAs, where it's possible, so that we can actually, let's say, then use like existing tools to accelerate machine learning. So we can run, let's say, at much higher throughputs. The challenge is the same in gravitational wave astrophysics. However, the data rates are smaller. The algorithms are more complicated. And so there we're talking about running on time scales that are, let's say, or data rates that are, let's say, gigabytes per second. And then trying to analyze that in real time. So using the analysis of the data and doing it with deep learning. So that's kind of our science driver, but then we wanted to make sure that we had kind of the computing and data intensive, let's say, tools to do this. So we brought in people from various groups in computer science, people who are experts at optimizing algorithm latency. So as you probably saw in Song Han's talk, and we also brought people in who are experts on algorithm design, such as Jane Zhao. And then we have people who are experts at two-scale computing infrastructure, and all sorts of things, such as Scott, who's on the panel. So the idea was to bring in various different experts and then use them to deploy deep learning to scale in high energy physics and gravitational wave physics, so that we can have, we can share in our experience deploying them, but we also share in kind of the whole circle of development, right? From starting from deep learning algorithms to putting them on a GPU or on an FPGA to running them in real time so that we can actually process the data. And so that's what this right column is. And then the point here is that we want to have a software tool that, if it works for these diverse applications, high energy physics and gravitational wave astrophysics, we can then deploy them generically to many different scientific problems. And so the goal here is to basically have a set of, software tools and experiences that we can then go and propagate to many different disciplines. And so that's why we, try to educate these people. In terms of, let's say, how we do this in terms of deploying, there's various different, we presented this actually quite a lot regularly at various different workshops. So you can see hands-on tutorials here that were done in NCSA. This was also done at various international conferences, including this week at the IML conference, the International Machine Learning Conference, which is a high energy physics conference. We presented a tutorial on Monday, the same time as this workshop. And actually, we presented a tutorial last week at the IEEE real-time workshop. So we've been trying to make sure that our software and our tools get presented like regularly. At NCSA, there's a weekly seminar series. And of course, we're trying to build a community here by hosting this workshop. So to just put some examples of things that we've done. So here are two algorithms that are used for processing of LIGO data. So on the left, you have a binary black hole algorithm, which reconstructs the waveform for the binary black hole, but also gives you various parameters about the merger. And you can see the predictions are quite good. On the right is a gravitational wave denoising algorithm, right? So this is for running real time on the noise data and then denoising it starting from just the raw time series inputs. And so this is something that you could, in principle, deploy at LIGO in real time, provided you have the infrastructure. And so this next slide is just examples of infrastructure. This is actually done with at the LHC, where we've actually taken various algorithms and we made servers, either FPGA servers or GPU servers, and we've deployed the algorithms in a larger scale computing infrastructure where we have, let's say, many CPU nodes. So just to show these plots, the x-axis here is the number of CPU nodes, right? And then the y-axis here is the total latency. This is running a full LHC real-time data processing, which runs at 100 kilohertz at the LHC. So it runs at the data rates are about a petabyte per, what is it? It's a petabyte per hour, something like that. And it filters it down to a petabyte per day. And so we've been able to run about 5 to 10% of the system with just a few additional GPU servers or FPGA servers. And in principle, we can run something like 500, let's say 300 nodes, CPU nodes with a single GPU server serving these nodes and running a specific algorithm. And you can imagine making many GPU servers running many algorithms and integrating to your existing computing cluster, right? This is the left case is GPUs, the right case we've done with FPGAs. And we actually were able to hit something like 1,500 parallel CPU processings served by a single FPGA for a specific algorithm. So the point being is that if we have deep learning algorithms, such as the nice deep learning algorithms we have for binary black hole merger or for gravitational wave denoising, we can then go to our existing computing cluster that's processing the data, install these servers, and we have all the tools to integrate this right in. So you can start to do real-time processing with ML straight away, and the tools are there. Yeah, this has led to all sorts of results. So you can look at all these papers. And then, this kind of brings us to what our vision is for a bigger scale institute. So in terms of a bigger scale institute, the idea our focus here has been on real-time inferencing. So processing the data real time and deploying deep learning algorithms to scale at real time. So we picked these two examples of gravitational waves and high energy physics, partly because they are in need of real-time processing. So gravitational waves, you need it for multi-messenger astronomy, as we've seen yesterday in many talks. High energy physics, you need this just because you have such a high volume, right? The data rates that we have are exceptionally high. And so you need to deploy AI just to keep up with the volume. In both cases, right, we're dealing with two slightly different problems, right? Gravitational waves often have, you're trying to solve, let's say, one very complicated problem, which is reconstructing the waveforms and denoising. Whereas in high energy physics, you're trying to solve many less complicated problems, such as, reconstruction of B quark, reconstruction of W jets, and so on. And so you actually, with high energy physics, you'll deploy many models. A gravitational wave, you'll deploy a few models, but you'll want to run both of these real time on the system. And so our view is that, well, we have two good examples and we have a real problem that needs to be solved. We want to be able to scale this out to a larger institute. And broadly speaking, our focus has been on, let's say, four main drivers, right? So the left driver is kind of our scientific motivation. So gravitational waves and high energy physics. But you can imagine adding other, let's say, domains where, let's say, real-time processing is critical. This can include fields of like material science. If you want to go off real time, you can imagine in climate science, there's doing a lot of, let's say, use of heterogeneous computing is starting to emerge. And you can also think about other fields where, heterogeneous like data throughput and processing data to scale on a large heterogeneous systems is critical. On the right, the point being here is that we want to make sure the tools are there so that, if you have a new algorithm, you can deploy it to scale at the edge, right? So you can deploy this real time, you can process your data. We saw this, for example, with the ZTF, is that they're trying to use as much heterogeneous computing as possible, because for relatively cheap, you can process a huge amount of data. And so our goal here is to make sure that we have tools that we can seamlessly integrate this to our existing computing systems and eventually, cause an evolution into how you actually design the real-time processing of the data. And of course, right, if we have tools, we need to educate people with this. So this goes not just, to making tutorials, but making sure that within our universities and abroad, there's let's say a literacy as to how to use these tools and how to really deploy AI at scale. And of course, right, all of this goes hand in hand with developments that are going on in industry, as well as the developments of going on in government, such as these new large-scale HPCs. And just to make a point of that, part of the reason we started developing kind of this infrastructure of CPU and GPU and FPGA servers was that the existing high-performance computing centers often consist of just the right side. Our old computing centers just consist of the left side, just GPUs. And there wasn't really a nice setup to kind of run fully heterogeneous. And in fact, we've tried to, or we have run on like HPCs, and it's been a little bit difficult because the infrastructure hasn't been there to run some sort of integrated system. And so the work we've been doing here is really to make sure that we can actually deploy this on HPCs and deploy this with our existing resources so that we can get the large throughput. All right, that's all I have to say for now.
Okay, yeah, thank you, Phil. Okay, so the next speaker, if Phil stops sharing, would be Scott.
I'll just keep sharing. So I think Scott doesn't have slides.
Yeah, apologies. I was a last-minute addition to this panel, so I don't have separate slides. I'm a faculty member at the University of Washington focused on FPGAs, high-performance computing, reconfigurable computing, and the like. I actually have started with Phil's group from a talk like 3 years ago when he came to the University of Washington and talking about high-energy physics that I knew almost nothing about, but he was putting up FPGA designs that I care a lot about and started going through what makes sense, what didn't, looking at optimizations, and kind of got pulled in to this overall program. And I think that's been one of the interesting things about this research project is that Phil kind of focused on a point in space that's kind of really interesting to a lot of us. It couples big data, real problems that frankly you can often explain to your mom about what the heck's going on, and you can explain to an undergrad and you can see the eyes open wide. So that becomes really helpful. There's also weird constraints, like most of the world in high performance computing would say, oh, batch things up into large batches, run on a GPU, you're done. And if you look at some of the applications like gravity waves, where's the multiple independent things coming from? The Large Hadron Collider, if you wait for a large batch, the storage is just ridiculous. So we have gone out and we've started working with industry partners, and frankly, that's gone really well. A couple of examples of that, we're working with Xilinx and the Fin team, which is developing a new way of doing neural nets on FPGAs. And I think to a certain extent, the important weird problems has kind of been this focal point that has brought them in. We've also been working with Microsoft and Project Brainwave, which is this, Phil had the picture of the servers and the FPGAs and all kind of working together, and that's very much what Project Brainwave is looking to do. This, I actually worked with the team for a few years. This was not the model we started with, but it's the model we kind of ended up with. So I think there's a lot of relevance to what's going on there. The team was originally thinking, oh, you have one server, one FPGA, they talk, that's what you need. And then you started finding everything's heterogeneous, everything's communication, and that became a much more important. The other aspect I will touch on just briefly is sort of the education side of the house, which is something that I'm fairly passionate about. I'm also at my department, the Associate Chair for Education. One of the interesting things from this area is that I think traditionally, so I'm a computer scientist by training, I teach electrical and computer engineering. I don't know that we've done a great job in training our students to be effective in this world of heterogeneous GPU, FPGA, multi-threaded, all of that. One of the things we're doing at the University of Washington, kind of in collaboration with this project, is developing a new BS-ECE, a Bachelor of Science in Electrical and Computer Engineering. And for us, we're going really deep into computing. And there will end up being 6 quarter courses on computation of some form, as well as advanced classes in GPU. But students will walk out with multi-threading, FPGA, high-performance computing, GPU, ML, data science. You come up with an acronym, it's somewhere in the curriculum, is where we're kind of at. I think one of the interesting things I'd like to do with this institute, though, is to look at how are we teaching computing and computational thinking to folks who are not going to be EEs and not going to be CS folks. But if you are a budding physicist, if you're a chemist, if you are a biologist, how should you be learning computing? What should go on in that space? My guess is if we look at a lot of universities, you'll find out that there's a single course in maybe C or Java, that's enough, and go off and then do what you want to do. There's probably at least a need to build literacy in what the options are. So I don't know that every scientist needs to be an expert in FPGA design, no matter how cool I actually think that is. But I think everybody ought to have an idea of what's there and some ability to say, okay, I'm working on this problem. I have a performance issue. This looks a lot like this or that or that. And you have a way to then go to the experts and kind of reach out and figure out what's going on. And I will tell you, as a domain expert in FPGAs, most of my most successful projects tend to have been because a scientist came to me. I'm here in this room because Shicha, about 6-8 years ago, came and said, hey, Large Hadron Collider, lots of problems, let's go look. And I had a radiologist who came to me and said, image reconstruction, really important, let's talk. And those types of synergies work, but I think they only work when the science community knows what's out there and knows how to kind of get to the right expert. And so something looking at what models of computing is, perhaps giving a flavor to these different things might be really important in kind of bringing HPC out to the real science problems. With that, I'll stop. Thank you.
Okay, thank you. So again, there's a link for questions, a document that's linked in the chat to have questions in, and we'll continue on to Eliu next.
Thank you, Dan. Okay, so let me just walk you through this. If you go to the bottom left, about 2 years ago, we organized a conference on deep learning for multi-messenger astrophysics at NCSA. And I got to talk with Eric about how we could do deep learning for gravitational wave detection. And he explained to me that Phil was working on something that was very closely related to real-time inference. And so we started talking about how we could have a multi-institutional interdisciplinary approach to tackling seemingly disparate areas of research with the aid of deep learning and innovative computing. And so in this publication, we started the process of community building. We talked, as we're doing in this conference, with different researchers across the States, Europe, and we listened to them carefully about what were the challenges that we had to address within the next few years to realize the science program of multi-messenger astrophysics. And 2 years later, here we are. We are again in the process of community building because we want to advance science with innovative technologies. And so over the last couple of years, what we have been doing in collaboration with Eric and Scott and Seche has to do with how do we go from just the conceptualization of an idea, which is let's use deep learning to address this challenge, to go and actually produce tools that can be deployed for this type of analysis, real tools, not just prototypes as we started a few years ago. And so to do this, we need to size the problem. And this is what Phil described in his slides. For high energy physics, you have massive data volumes. For gravitational wave astrophysics, we have high dimensional data sets. So different problems. Yeah, exactly this. And so if you go back to the other slide, Phil, something that we started doing to try to address this problem of high dimensionality, which translates into big data sets to train the neural nets, is what resources do we have at hand to do this type of work? And so we started collaborating with our colleagues at Argonne National Lab, and they have a program that they call the Data Science Program. And the first year that they had a call for machine learning projects, we submitted a proposal and we got time in their supercomputers. And so we started working with them to deploy these type of algorithms on their supercomputers. And it was a fruitful collaboration. We not only developed the algorithms to design neural nets at the scale and incorporating physics-inspired optimization schemes and how you correct the architecture to incorporate your knowledge into these neural nets. We went the extra mile, if you want, developing the tools to learn about how neural networks abstract knowledge from data, something that is important in the angle of interpretability. So when someone asks you, why do you trust that the neural net is making the correct prediction? Or do you know what sector of the architecture is involved in learning and in the prediction? Well, a way to try to address these questions is through scientific visualizations. And this is something that we have been doing very actively. Now, we also realize that in addition to just developing algorithms for real-time detection, or actually for forecasting the existence of signals in advanced LIGO data before, for example, neutron star mergers take place, which is important for multi-messenger astrophysics, we understand that we need to go beyond this. It is not just algorithms for real-time detection or forecasting. We have other challenges in multi-messenger astrophysics, and which are these? Well, in the visualizations you see in the middle related to neutron star mergers, the other challenge that we have here is that these software stacks for numerical relativity are computationally intensive. For example, just to present the two extremes of the spectrum, when you want to model black hole mergers, you can finish a simulation in a couple of days. When you want to simulate neutron star collisions, this can take you months. So if there is a new detection, and you want to go and sample the parameter space of possibilities that may produce some type of electromagnetic counterpart, you need a lot of resources. And so the other angle of our program has to do with accelerating these software stacks with deep learning. And so in the middle of the slide at the bottom, you see some recent work in which we are using deep learning to accelerate the modeling of subgrid scale processes like turbulence, which are very relevant for the modeling of neutron stars. So here you start to see the emergence of this picture, which is deep learning not only for gravitational wave detection or forecasting, but also to model these complex sources, okay? And it is this type of activities that also go into interpretable AI that have given us an opportunity to interact with other members of the community. So with Brad Whitmore, with Janice Lim, we have been working on doing translational research, how we apply these tools, for example, for the classification of star clusters observed by Hubble. Or here at NCSA, working with people that are interested in classifying images taken by NASA satellites. And so one of the challenges there is to tell apart clouds from ice. And so we have been working with them, applying the tools that we have developed for gravitational wave astrophysics to do this type of analysis in geosciences. We have also been working with colleagues in medicine, combining the algorithms that we developed for gravitational wave denoising and earthquake detection to identify hard conditions in ECG data in real time. And so the vision that we have for this institute is that even though all these areas look disparate, actually they are threaded by the same challenges. And so we want to make the center a place, or the institute a place where we can do translational research. And so the vision for this is we have some areas that share common challenges: gravitational wave astrophysics or multi-messenger astrophysics, high energy physics, geosciences, and foundational AI. And so all of these can be housed within the same institute. And all these areas will benefit by cross-pollinating the expertise that we have in the different domains. And you can see that the actual thread that is going to unify these areas has to do with innovative applications of machine learning and computing. And one of the things that we want to develop here is an understanding of really the different algorithms that we are using. Are they really that different? Or we are just going through the easy roads of developing new architectures as we see fit? And so one of the things that we want to explore is whether we can develop a better understanding and then develop commodity software. So this way we don't have to be developing algorithms every single time we want to solve a problem. And so this will only be accomplished when different experts bring the challenges to the table, and then we look at them from a high-level perspective, not from the vision of, I have this problem, give me any neural net to solve this challenge that I have. So this is how we are envisioning the creation of this institute. And as you can see, we're already building up these synergies with different experts, different disciplines. And it is through these discussions that we want to move forward with an informed perspective of what are the real needs of the community and how this institute may help address them. So that's what I have done.
Okay, thank you. So the next speaker is Raf, I think.
Yes, I'm going to share my screen. And meanwhile, I've been asked to give a little bit of a perspective of on what AI can do for the field of LSST and time domain astrophysics in general. Can you see my screen?
Looks good.
Can you also see your faces or not?
You can see faces either on the top or the side, depending on how people are viewing, but it's not on top of the.
Let me do this. Okay. Yeah. So yeah, I'll try to give you my perspective of what AI can do in the world of time domain astrophysics. And here is as an astrophysicist, here is how I think about the problem. So what I will try to do is to try to put on this phase diagram of luminosity versus time scale, the places where I do believe there is a lot of potential for discoveries. And then I'll try to lay down what I believe are the needs to get there. So how do we really enable discoveries? So you have luminosity versus time scales, and t equals 0 is when your favorite transient will go off. And this line just shows you the typical luminosity of our most normal transient, a supernova. And then I will put here some time scales that will be useful to guide our discussion. So there is a portion of this parameter space that we've been extremely good in sampling so far, which is unsurprisingly the one that is mostly connected to typical luminosity and typical time scales of supernovae. And there are, though, other places where we have not been as good. In the era of LSST, if I have to think about it, the place where LSST will definitely do extremely well is in the pre-supernova phase. So what I mean is the following. We have a new transient in the sky. All we have to do is to use all the images that LSST has accumulated during the years and see what happened there before explosion. We do know it's a rich area for discovery. It has not been sampled that well so far, and this is where LSST is going to give us this view for free. I do not believe that there is a special need in this area. And I'll move on. The other place where definitely there will be tons of discoveries in the future is on the other side, so the very, very late time. And particularly here, I am referring to spectroscopy that will be enabled by the extremely large telescopes. So again, here is a place where AI, I don't see a huge role for AI, but it will definitely be rich for discoveries. Another place of the diagram that has not been sampled very well is the one that is connected to a very fast transient. So very fast means something that goes up and down over timescales of days. So these transients are not really known what is the physics that is going on, mostly because we didn't have the capabilities to find them. And to be very, very open and fair, the main survey of LSST is not going to help us much, and AI can't help us there. But if we think about the deep drilling fields of LSST, so those fields that LSST will revisit way more often than the average survey, this is a place where LSST can really make a difference, and AI can make a difference, as I will explain in a second. These transients, these very fast varying transients, are also extremely rare. This allows me to introduce a key element of LSST. LSST goes deep, which means that LSST buys us volume of the universe that we can investigate. We have the opportunity to really find the rarest of the rare transients. So what I can show on this diagram is this third dimension of how common these transients are. But let's keep in mind that one of the areas that we want to try to explore with LSST is very rare events. And later in the slides, I'll tell you what we can do there. And then, of course, the other place where everybody is thinking about trying to make some progress is to find counterparts to gravitational wave sources. And as we will see later in this talk, this requires a completely different mindset and view because of the way the trigger comes to us. And it became clear in a second what I mean. So if I have to oversimplify the way that I think time domain astrophysics will benefit from AI, here they are. There are two ways we can make progress. So the one on the one end, we will have the possibility to do very large sample studies. Consider that when we say large samples in the world of time domain, it means 1,000 of events. It's not the very large samples that we people are thinking. So right now, this is where we are right now. LSST will allow us to do the next step in this world. We heard from yesterday from a couple of talks saying that LSST can in principle find millions of supernovae. So one thing that we can do is, okay, we can collect all these light curves that LSST is going to give us, and then after they have been collected, we can do classification based on almost complete light curves, and that can definitely provide a view of a population study that is currently missing in the field. This type of approach is sort of self-contained in the sense that it doesn't need more data. If you want, you can play this game after you have collected your data set. So it's not as time critical. Yet it does benefit from AI in the sense that we will have to learn how to classify things based on this limited information. And we have been having a couple of talks, very interesting talks yesterday already about how to do that. The other way to advance the field is more of a completely different direction of saying, instead of doing population studies, I go after the new stuff, so the rarest of the rare events that we still don't know they exist. In this case, what we do need is a fast, reliable identification that something is there in the sky for me to look at. And that is actually very much connected to anomaly detection. Monica Streisand yesterday told us something about her efforts to do that. The other need in this case is to be able to reliably reject contaminants. What for me is contaminants is probably very good stuff for some other astrophysicists, but what we mean is that out of the thousands of events, you need to find the n=1 event we are interested into. This, a second way to advance the field, does require in real time a discovery engine to feed the follow-up machines that will allow us to do the physics. So AI, I believe that these are the two main ways that we will see time domain astrophysics to advance in the next few years. And as you can clearly guess, these two ways do require completely different AI efforts. So let me focus a second on this second type. And all we want to do is very simple. We want to go from here to there. That's very clear. So how to do that is lasso. So in the community, there are right now two main ways to try to play this game. And the one, maybe the most common that's been used so far, is light curve classifier. So trying to guess what things are based on very partial information about what the transient is doing, based maybe on a couple of data points. And as I said, what we want to do is really try to guess what things are at very early times, because this is a place where we can find new things. Less common strategy that has been applied at least until now is that of using all the information that is known at that location in the sky. This is what we refer to as contextual information. This is what we started doing thanks to a grant from the Simons Foundation. And what the principle is very simple. What we try to guess what the transient is based on everything we know, ideally everything we know about what's going on in that place in the sky. So both what the transient was doing before the explosion, but also in which type of galaxy that went off. And again, I'm going to oversimplify, try to highlight the most common needs of the field here. So contextual information means effectively based on where you live and tell you who you are. And among all the features that we can use to play this game of identifying transients, we know by now that one of the most meaningful is the redshift, so the distance of our transient that tells us the intrinsic properties of the transient itself, which brings up the need for reliable photo-Z's in the local universe, where local means, let's say, 100 megaparsecs or less. So it's really local. And we do know that that's a place where we do need to advance the field. The second is host galaxy morphology, which is a proxy for, if you want, for how old these stellar populations are, or if you want star formation rates. And then the third feature that we know is very predictive is the distance from the host galaxy center. So all of these three main properties that we can use to classify transients right at the time when they happen, they do rely on one thing that might seem a little bit silly, but it relies on us being able to associate a transient to its own host galaxy. And sometimes, as if the transient is nice to us and happens nicely inside the image of a host galaxy, as you can see as an example that I picked, that seems like a very stupid thing to do. Yeah, clearly that transient most likely is associated to that galaxy, but sometimes nature is not so kind, and actually in most of the cases we are in the situation of that a yellow star that is in between two galaxies and is not as trivial. Yes, I got the heart. Not as trivial to understand where the transient belong. This is another place where we can use AI to help us solve the mystery. So to put everything together, I want to save a couple of minutes for gravitational wave follow-up. What we need is putting all of this information together, light curve classification as it happens in real time, contextual information, and produce the synthesis of our, if you want, the probability of the transient being this or that, and develop what in the literature is now being called a recommender engine. And here I refer to one specific developed at Purdue that will allow the scientific community to make informed decisions on where to point their telescopes. That's what we want. So let me use a couple of minutes to tell you what are the needs when it comes to do follow-up of gravitational waves. And here I put on my hat as the chair of the gravitational wave follow-up subgroup within LSST TDS. So first of all, so why we need LSST to start with? What you have there are light curves. There is one take-home message from this plot, which is they are faint. And you can see that we really need LSST in the depth that we can reach with LSST to have some possibility to find kilonovae within 200 megaparsecs. There is no other game in town. So why we can just rely on luck, meaning why we can just wait for LSST to serendipitously cover that field, because if you do numbers, that gives you a 7% probability to cover that area of the sky, and that comes with limited color information, limited coverage. Then there is, of course, weather, meaning that most likely we will not be able to do our science. So we do need target of opportunities, which means we need to interrupt LSST and say, hey, for now, for the next 5 minutes, you stop what you were doing and repoint that particular place in the sky, because LIGO has just told me that something interesting is happening right there. So the other approach that's being used for 17-17, for example, was to repoint specific galaxies in that area. That is also not a good idea when we will deal with way farther targets, just because there are too many galaxies in the field. So where is the frontier? After we found the first electromagnetic counterpart to gravitational wave sources, where is the frontier, where we want to go, and how we're going to get there? So I don't have the time to walk you through all the 5 points, but the bottom line is that we need to go deep and cover the entire area of LIGO, and that's why we need LSST, and we need to do it very, very fast and get color information. We have proposed and designed a potential LSST target of opportunity strategy. I would like to emphasize that there is no formal word that I'm aware of TOs being really implemented. It seems very likely, but it's not known for sure. This is my last slide. So the game that we are trying to play in here with LSST is using LSST as a follow-up machine. So Mario yesterday actually introduced this concept. For everything else, LSST is a discovery machine, is the one scanning the sky and tell us, hey, there is something new there. In this other case, for gravitational waves, it works the other way around. We get the trigger from the outside world, LIGO, and then we repoint. LIGO, let's assume that LIGO gives us this gray localization region. We have a number of potential electromagnetic counterparts, and only one is the right one. And what we need help with is to find a reliable way to just throw away most of the contaminants and focus on the most promising counterparts. So rejection of the contaminants is the place for AI to play a role for the EM counterpart game. I also want to emphasize that we do expect the localization of the gravitational wave sources to improve dramatically in the next few years. So what I'm saying is that while I do believe that to play the game of transients in the LSST era, we do need a new infrastructure, I'm not convinced that if the error localization region shrinks so much, I'm not convinced that we need a completely new infrastructure for gravitational wave follow-up. Meaning that we have been playing the game of following up gamma bursts for 30 years, and here the number of sources is even less, it's way fewer. So the community is ready to do that. Final point, we talk a lot about multi-messenger astrophysics. I would like to emphasize that before moving to MMA, we need to remind ourselves that there are other photons apart from optical photons. And I would like to see first scaling from optical astronomy into multi-wavelength astronomy, and multi-wavelength astronomy to be fully integrated into MMA efforts. And that's it. Thank you so much. I know I went over time.
Okay, thank you. So Patrick is next and last in the formal talks.
Okay, so I'm just going to tell you a little bit about the SCiMMA project, where we're at, where we're going, and sort of what our current vision is for an institute that might be formed around multi-messenger astrophysics, but could be broader. We've already heard in the past 2 days, and just right now from Raf, we heard a nice discussion of where multi-messenger astrophysics lies in the context of astronomy. And I threw up this slide just to remind everybody of that. When we've been thinking about it from the SCiMMA perspective, we kind of consider there to be sort of 3 anchor facilities around the MMA, we're thinking about IceCube, the Neutrino Observatory at the South Pole, LIGO, Virgo Cagra, the gravitational wave detectors. And in this decade, we're expecting Vera Rubin Observatory, so LSST, to also be an anchor facility within the US on this. Now, one of the big questions is why go for SCiMMA now? And well, there's sort of all kinds of answers to that question, but I think the most compelling is that we've seen how we can now go beyond the photons and go out to include other messengers like gravitational waves and neutrinos to understand the universe and get a full both sight and sound, let's say, of the events that are going on. And it really does help us to complete the story of the objects we're seeing. Now, I did want to go back, and this diagram is overused by the multi-messenger astrophysics community, but it does tell a good story. And for those who may not have seen it before, I want to just give you a sense of what's contained in it. The first thing is up near the top, you've got the gravitational wave discovery, and then the horizontal axis is time frame. You'll notice that there are two different time frames. There's the seconds time frame that is on the far left, and the second time frame on the far left, and then the days time frame on the right. And that days time frame stretches out to months and even a year, even beyond a year. And then you've got the full spectrum of electromagnetic waves as well present on it. Each of the dashes that you show going across this image actually indicate an observation that was reported in a given band in an attempt to identify the object that we were looking at. And in fact, most of these are actually targeting the correct associated electromagnetic object. But what you can see is that if you digest this diagram, you notice that there's activities going on all sorts of timescales, from seconds to minutes to hours to days. And it goes on across just a huge spectrum of facilities that are spread out around the world, have all sorts of different ways of actually managing how they look at the sky, come with all sorts of challenges when you try to do multi-messenger astrophysics. So if we think about some of those challenges, what we have is we've got heterogeneous facilities, heterogeneous data, and heterogeneous people. The data is usually relatively high volume and high velocity, certainly at the early times. One of the things that I think is key within multi-messenger astrophysics, and actually any time domain astronomy, is that there's actually often quite rapidly developing and dynamic collaborations. People who know someone who has access to a particular facility to make an observation, little contacts are spun up, spun down. As a result, there's heterogeneous data sharing policies. There's competition for follow-up resources. If we want to do better than we've been doing up to now, which we always want to do better than we're doing up to now, you need to do rapid modeling to do more informed scheduling decisions. And then finally, for this type of transient astronomy, which is dynamic, you run into this tension between human and machine communication. The more things that you can automate at the machine level, the faster you can go and the more resources you can bring to bear. On the other hand, we need to understand what we're looking at. So we need a way to digest and assimilate that information. Now, we've got within the SCiMMA project formal, but we're actually trying to be more broader and involve much more community engagement in the last 12 months or so. We've got plenty of representation across all sorts of areas. So I'm not going to go through this list. You can read it later. This is just existing cyber infrastructure for that's mostly focused on transient astronomy, but the point is can be brought to bear on multi-messenger. So what have we done as the SCiMMA project within the past year or so? We've been focusing on two things, community building and prototyping, with a view at the present time to move into a phase of trying to conceptualize what an institute would look like. So this meeting today is, and this panel is actually a good opportunity to start brainstorming with other possible collaborators. You heard a lot from Mario yesterday on the different activities, but I wanted to highlight hopscotch as one that is this sort of gap that we identified in the community for communication to be able to provide reliable message passing at scale. And so we've worked to try and to develop a prototype to demonstrate how one can bring to bear certain types of software development tools to build out systems built on standard now technologies rather than reinventing the wheel. And this is beginning to have some broader impacts also. For example, it's being used out in California as part of a baseline architecture for communicating between sensors in the field to monitor rainfall, to monitor humidity, to understand irrigation, and so on. So there's a lot of power in a communication system like this if it can be brought to bear. As I mentioned already, we've been broadening out our community engagement. We've now had basically twice a month we're having meetings with various people from the community presenting on topics. We've had presentations from Phil and Eliu and others. We've got a collaboration going with the SNOOS project, and that's connected a little bit through the HDR Didax project that you heard about yesterday. I've got just a number of little places where we've got things that are ongoing that we have connections made. If you want to look at any of these things and sort of maybe skim through them or listen a little bit to some of the presentations or discussions, they're all being posted on YouTube. I wanted to highlight this slide from yesterday's talk by Mario, because this is actually sort of the next direction we want to go with prototyping. And it's this idea to, now that we've got a communication system, we've also built out an authentication infrastructure that we can use to build up and spin up and down collaborations. We want to take a next step towards this idea of having data lakes for information so that you can get the data to the place where you need to do the compute and so on. And so this is just a sort of, we're only just getting involved in this. We had some discussions the other day where Gautam Narayan was presenting and discussing brokers and brokers in the LSST era, and he was emphasizing this as a path. And so I think, again, this is a new direction that we're going to go for prototyping and trying to demonstrate what power of an institute could be. Within SCiMMA, we've had activity areas that include systems, data management, innovative algorithms, which is the inference, machine learning, and so on area. Now, I would say compared to this workshop and the efforts that are going on in the other collaborations that are and HDRs that are out there, we have not emphasized machine learning as a key top priority component of ours. But the synergy is obvious. It is absolutely clear that machine learning and AI has plenty of power. A thing that hasn't been mentioned here today, but one that we've been curious about, is that when you've got this heterogeneous network of telescopes and you need to actually submit observations, one can ask the question, are there ways that you can actually do smart scheduling to figure out which observations to take and when? And this is almost screaming out for a fairly, I think it's a tough project, but a project to look at it with machine learning and AI to see if there's actually benefits. We have a modeling and theory component that we've discussed and figured out areas of synergies there. Education and workforce development is an area that we're really beginning to put together our ideas much more strongly. And Dan, I see the heart. And the goal there then is to actually figure out how to do training. And there's again a big synergy to the remarks earlier about training and workforce development that we need to have. So what do we have in mind as a mission for an institute? Well, it's to advance and accelerate discoveries in multi-messenger astrophysics by catalyzing development of a data science ecosystem that includes operating discipline-specific cyber infrastructure, codified knowledge processes, and building a diverse and engaged community. It's a mouthful, but at least it's only one sentence. The second slide that I have about an institute vision is this one. And this was put together by Margaret Johnson and Don Petrovic as a way to try and think about how an institute sits within the context of broader communities, facilities, and other things. And I really like the way the end goals, for example, are called out in this. So for the scientific stakeholders, the users, the people who are the community that we all are, but that an institute would serve, their goal is actually development of knowledge. That the institute would have this goal of assimilating information and organizing information and providing easy access to information. While there are data sources which are the primary instruments, and they actually are the sources of data. So their end goal is to deliver the data. Anyway, this structure is sort of a high-level view for what we think might be a strategic roadmap to an institute. One thing that's maybe not so obvious in this is, again, where the innovative algorithms fits in. But again, we really think that within the context of any HDR institute, it will really need to embrace innovative algorithms and the artificial intelligence and machine learning. So with that, I'm just going to finish so that I don't go over time by too much, and leave up just a couple of links for people if you want to take a look at them.
Okay, thank you. So at this point, if we were all sitting together, we would have a round of applause for all the speakers. So I'll just say that virtually we'll applaud all the speakers, so thank you. And we'll go on to some questions and discussion. At this point, there's only one question that I see that's been added to the document. And so I'd say, John, do you just want to go ahead and ask your question?
Yeah, sure. Thanks for all the presentations. I just had a question for people who are working in smaller research groups. The previous solutions from past years has been often to just rely on your own server, like building custom hardware and stuff. And even if you're scientifically minded, like I work in astronomy, it would be typical, say, if I needed to do data reduction for like radio telescope observations, it would be like, okay, we're going to go find some funding to hack together a server, and then that will be like the research group server. Of course, that paradigm has changed for many folks, especially working in like the supercomputing realm, or like needing like to scale up their compute. But for small researchers, research groups, does it still make sense to try to purchase your own hardware, or should you basically be relying on flexible compute from like cloud and other servers?
I can comment from the LHC perspective, which is that, in fact, the funding agencies, I mean, usually you have to get funding to make a server. And the funding agencies, and this has been a big deal within the LHC community, that they don't want to fund kind of local computing resources in the future. And so, I mean, which is in some sense good, is that you have to now kind of use existing or rely on tools and use the HPCs. They're building these very large HPCs. So you have to, reserve time on them, but they're in principle, the amount of computing is quite large. So how you integrate this with the HPCs is another interesting challenge, right? When it's not, it's not clear you have necessarily the right resources to do this. So that's kind of, how we do this in the context of high energy physics is actually kind of one of the reasons, I've been doing this work is that, we wanted to use HPCs, and the HPCs were not really, they're kind of designed for large scale simulation. So like Eliu was talking about, before machine learning, these large scale gravitational or binary black hole merger or neutron star merger simulations. This is the kind of thing an HPC is perfect for, right? It was designed for solving, large integrated differential equations. If you want to just process a lot of data, it's not really, or with small algorithms, it's not really designed that way. So we have to rework things in a way that you can do that. But I mean, you know, it seems like this is kind of the trend of where people are going. And so figuring out how to exploit the HPCs is kind of a critical thing. Another thing to say, right, is that the HPCs are at the moment heavily going to GPU. And so that kind of forces you to go on a paradigm where GPUs are, you know, processing of your data with GPU is fast and efficient. And so you have to kind of rethink about how you do this. And kind of a natural way to do this is to just do it with some deep learning based algorithm. But certainly it's not necessarily the only way.
Right. So Patrick, did you want to respond to this as well? Is that why your hand was up?
Yeah, I was just going to say, Phil touched on many of the things, I think, and I agree with most of the points. I do think, though, it's like everything. There's actually multiple tools. Sometimes you're going to need a local server. Sometimes you're not going to, you're going to need HPC resources. Sometimes you're going to be able to scavenge. Sometimes you'll need dedicated machines. So the question's not there's not just a single answer to it. It really depends what you're doing and at what scale.
Okay, anyone else of the speakers that wants to respond? Or we'll go on to the next question.
So I'll prod Phil a little bit. The other thing I think we've seen in the work is that packaging the data up and going to a cloud server has worked surprisingly well and can support surprisingly high rates. So it is, from what I've seen, it's much more practical than I would have expected going into this.
Can I actually just press on that for a moment, because I'm interested in, it's the first time I've heard a positive statement to that effect. So in terms of costs, have you basically, how much data are you pushing in and pulling out? And so is the claim that it's cost effective at a standard rate from the cloud services providers, or it's cost effective when they give you it for free? So where do we lie?
Scott, I guess you want me to comment. Yeah, so the cost. Let me say it this way, is that we started with the cloud because it was free for us. We had some resources from various grants. That being said, right, the cloud was, I mean, once you got things working, it works really nicely. So, you know, you could do a cost analysis. I would say that, you know, we did this. I would say that the conclusion is that if you wanted to run long-term, like large scale, it's not cost effective, right? At that point, you want to go to an HPC or, you know, build an HPC, but for prototyping, it's actually quite effective because it's very easy to then, you know, you can start with like a little, you know, small set of stuff and do R&D on that. And then you say, oh, you know, we're going to run this on a 10,000 core system. You can scale that up, run it for an hour or two. It's not going to cost that much. And then you have, you know, a full prototype. So for prototyping, the cloud is, I think, fantastic. For long-term running, that's not necessarily the case. But the nice thing is that you have these HPCs, so you can take what you learned in the cloud and bring it to the HPCs. And that's kind of a project we're starting now. We're thinking about how to do this. It's been interesting because, like, you know, some HPCs, like, for example, they just don't support the same software infrastructure you can get easily on the cloud.
Okay, so let's go on to a different question at this point. So there's a question from Eric that's for Patrick. So Eric, do you want to go ahead?
Yes, thank you. First of all, thanks to all the presenters and the panelists. This was a very helpful to set the stage for the discussion today. Now, I'd like to pick up from where Patrick was left. I put something in the document, namely the fact that there has been around for many years, decades, multiple efforts in order to build this kind of brokers, this kind of standards on how to exchange and archive data, Patrick. And many of them still remain in use as we speak, depending on what kind of wavelength you use in the electromagnetic spectrum, or what kind of source you're after, or even neutrinos and gravitational waves, as you know. And of course, even differentiations among those three, depending on where you are around the world. Now, where would you describe SCiMMA to be falling into that landscape of today? Do you envision some organized effort in order to consolidate those existing schemes and efforts? And I was wondering rather whether there has been any effort to, let's say, have pre-subscriptions from big projects and big contributors in that machine you're planning to build, or you're envisioning materializing.
Yeah, so I think the first thing is that we've tried our best to stay away from standards definition and trying to and redoing those. We've taken the attitude that if you're going to try and create some sort of standard or interoperability, you've got to basically have software that implements what you're doing, and that's where we sit. We don't want to supplant anything that already exists, so our goal is not to do that. In terms of, if you take the hopscotch example, where we've built this communication system right now it's built on top of Kafka, but it's meant to provide essentially an API to a reliable messaging system. Our purpose for that is that we've seen a gap. LIGO would like to be able to get its information out faster and be able to have it consumed in a way that users can easily get to it. They know how to interface it. They have a good client for it, and so on. LSST, we work with Mario Jurich, who's part of LSST, and we are tightly coupled in with the Kafka development on LSST, but we're not trying to supplant or overtake it. On the other hand, by having certain types of simplified software interfaces to messaging like this, you can actually allow the community to ramp up much more quickly. Our goal, if we look at where we want to, we think an institute can have value, is in really helping to modernize various tooling that exists out there. It's easy to stand up a web page that writes some HTML, dumps some file on disk, updates it based on a cron job that parses an email that comes through every so often, right? However, that's not really sustainable. And there's some best practices for making sustainable software, for building sustainable services that we'd like to bring to bear. So what we imagine doing is, one of the components of what we've been thinking about an institute should do is there should be a means by which community members can get some funding for fellowships. And so we really see this focused on students and postdocs for the most part, who would work with some professional staff for some period of time to either initially prototype some software or prototype some methodologies or prototype getting it onto some computing architecture or whatever, and then to learn what the best practices are in that area. So we're not talking about supplanting. What we're actually talking about is trying to find a way to improve the sustainability of tools and software that are developed by the scientific community, and to train up the new generation of students and scientists to know what the best practices are for those. On top of course, the Hopscotch is an example of a service that we could stand up initially, but we also don't see that necessarily as something we have to own long term. If a different entity said, that really does have value and we really want to step into that space and we're willing to take over maintenance, this is great. We can hand it off and move it that direction. So we really see ourselves as trying to be innovative, include and improve sustainability, and try to help the community move towards some more common standards, and by providing software tools that can be used across the board.
So let's see. So we have a question from Michael also to Patrick. Let's see if we can do this one quickly, because then the question from Adam, I think, will be a better discussion to include more people and maybe kind of wrap up the panel. So Michael?
Oh, it's fine if you want to jump to Adam. That is perfectly fine.
I mean, go ahead. You were there. You're here, and it's a different question.
Okay, so to Patrick, latching on to the point about sort of feedback into ongoing observations within the community, how do you envision building an institute that has enough of the right members of specific projects involved, i.e. the leaders in the areas that drive the decisions being made, for example, in gravitational follow-up, of course, to ensure that this, the institute has access to the type of and the data, the quality of the data it requires to push forward the science that it wants to see done?
That's actually a great question, Michael, because I think it actually will highlight something that may be a little surprising. So our vision for the Institute itself is not that it actually does the science. Our vision for the Institute is that it takes on a task, which is again a gap. It is the providing the tools that are missing and providing them in a sustainable way, providing the training that may be missing and providing that in a sustainable way. And then providing services, which in fact, part of the reason we've gone to the trouble of standing up an identity and authorization infrastructure that's flexible and that is modern is that we know that the data is going to have differential access, and there's just no way around that. We just can't change that. So that has to be built in from the get-go. You notice that I highlighted one of the challenges of multi-messenger astrophysics, and I think it's true for transient astronomy or any dynamic field which involves sequential observations, is that collaborations are very dynamic and they tend to have all kinds of different rules. You can't anticipate how anyone's going to interact. So what you need is a supporting infrastructure for that. It has to enable that. It cannot sort of require a certain approach. So we're trying to take this enabling approach rather than the requiring approach.
Okay, thanks. So so Adam, I think your question that's up there, I think is good, and potentially maybe we could go through the speakers in order if they choose to from the way they spoke and see what answers they have. And let's Adam, can you go ahead with the question?
Sure, yeah. So by my background, I should tip my hand. I'm the chief architect of SCiMMA, so I already have. We've thought a little bit about this, but so my question is to everyone. So how does the Institute work with the broader community, which consists of experiments, observatories, and also a lot of PI researchers, to incorporate their expertise and output while maintaining a clear direction? Because the Institute is a long-term thing that will be going on years and years. And sort of related to that, or perhaps more generally, how does it decide where to focus its effort and resources, year on year?
So Phil, do you guys?
Sure, I can start. So how does an institute? So all right, I mean, I'm trying to make this. I'm going to put this in the context of. So I'm in this AI institute through MIT. There's a physics AI institute there. So there, and we were successful. So there, the strategy of tying things together was to make it clear that PIs are going and doing their research in various collaborations or, theory or whatever they're doing. But the part that was centralized is to do machine learning that's physics motivated. And this is true. And we found computer scientists who do this, and we found physicists who do this. And the point is to kind of force a discussion around this single topic. And it's not, you do, if I put out a paper that's, let's say, some machine learning algorithm, right, then it's part of the institute. If I put out a paper that's, measurement of Higgs boson properties, right, then that's not in the institute, right? And so you keep kind of a central focus. in terms of, how you change the focus, in the case of the Physics Institute, we decided to keep it, as physics and AI, and that doesn't change. Now, stepping into an HDR, right here, in this case, right, kind of the things I see that go across fields, right, which is, I think, where the Institute would have power, is various, in this case, it's various, I don't want to call them software frameworks, but kind of ideas, technical approaches that are consistent across the field. So you could imagine, right, a challenge, right? You do the SCiMMA challenge of, let's integrate all of these telescopes and new gravitational wave detectors in the next year. However, I would think that challenge at some point goes beyond the scope of the Institute. The Institute is more, can we make sure that the software is robust to support this project? Because I can give you an equally, let's say, difficult project, right, in high energy physics, or an equally difficult one when Dune comes alive, in neutrino physics. And I wouldn't say that the Institute should focus on any of these, right? But they should make sure that the infrastructure is there to support all of these. So I think that's kind of what we've done here, where, if you have, for example, accelerating ML, right? The plots I showed were for high energy physics, but we have equivalent plots for, gravitational waves, and equivalent plots for actually running proto-Dune. So it's really the focus here has been on the infrastructure. All right, so I think that's all I'll say.
Okay, Scott, any comment?
I'm going to defer to those who've had more experience with this. This is the largest one I've had anything with.
So,
okay. Eliu, then?
Yeah, one more thing is you can see some corporations that have been very successful engaging with the broader community. Like, for example, those developing neural nets from Google and from other efforts like ImageNet. So one thing that we have envisioned to engage with the community is to be open about the tools that we are developing. That this commodity software that we are developing is readily accessible to the parties involved, stakeholders. We are already doing that through the Data and Learning Hub for Science. We give people tools that bypass the need for example, access to high-performance computing machines, or the need to learn distributed training and all of that. So we are doing that on their behalf. We offer the algorithms that they need, and then they can go grab them, and then through very minimal work, they can adapt these algorithms to their needs. At the same time, we enable them to interact with us. So there is this ongoing communication so that they can participate on the further development and improvement of these algorithms. So open source science is at the heart of meaningful collaborations with other communities. We will also have an advisory board that will represent critical efforts for the institutes. And we will continue to have these open events where we go and hear from the community and refine the type of efforts that are well-defined, but we know that the community will continue to evolve. So the goals that we have for 1 year will be updated and refined based on what the community needs, right? So we are not following just abstractions, but we are actually addressing the needs that the community has. And at the same time, something that is critical, and we are emphasizing this, when we are developing a skilled workforce, we are going to make sure that students, postdoc staff have the opportunity to go and engage with industry through internships, stays with different companies that we have at the moment, like NVIDIA, IBM, JP Morgan, Goldman Sachs, etc. All of this so that the students have a global vision of what it means to apply AI to solve difficult challenges. And then we have a virtuous cycle of cross-pollination. Academic innovation goes into tangible benefits. We learn what these companies are doing to tame similar challenges, and we incorporate that wisdom into our projects.
Okay, thank you. Raf, any comments?
Yeah, I think Eliu already did a great job. I don't have the experience of being part of an AI institute myself. If I can, I completely agree Eliu. And actually, I think my presence here is probably maybe the reason why I'm here is to have the LSST and time domain EM community to have a voice and tell you, hey, this is what we would really need. Can you help us out? So I think that's exactly the type of feedback there that Eliu and the others were describing. So thank you for having me.
Okay, and Patrick.
Yeah, so I personally think this is a critical aspect of any institute. We've had a few discussions with some of the SSI management teams for the software sustainability institutes that they have, and we've sort of been thinking about this a little bit. What's absolutely clear is that meetings like this one, workshops where you actually take a look at the landscape and take a sort of a roadmap assessment. So see what's going on and try to take a look for a roadmap for the next year, maybe for the next 5 years, who knows? But you have to do those. So that's a key component. The second thing that I think is actually very important and is an interesting approach, this is actually what's done by MALSI, which is the Molecular Science Institute. They have a professional staff that does the software management and development. But in order to figure out what those staff work on, what they do is the staff are given a couple of months, every once they've wrapped up a project, to engage with the community and to explore and find out what the community wants. So they go around to different partners, to different groups that have engaged already, and they check in and they ask what software they have, what problems they're encountering, and so on. And what they do is that they essentially try to build a project that they think is a good one for them to focus on for the next phase. And that apparently has been quite successful as a way to figure out the right things to do. Almost, from what I've heard, it's been better than the road mapping, because the road mapping tends to be a little bit loosey-goosey in a sense, I would say, unless it's very, very strictly focused. The third piece that we think is an important component of an institute is related to fellowships. Any institute's going to have to serve the broader community. It cannot be limited to an institution or a small set of institutions that host all the postdocs and students, and that's everything in a single place. For MMA, it's just absolutely obvious because it's stuff everywhere. And so we know this is the case. So what we've thought about is a set of fellowships. They'd be targeted towards students and postdocs. We're looking at two timescales for those. One is a sort of a short-term fellowship that might be of order a few months, up to 6 maybe, which would be some project that needs assistance from professional staff to understand how to get past go, how to bring things to the next stage or whatever. And if they're successful, so if they're kind of a good match to the needs, if they're shown to be viable projects, if they seem to match community expectations, then the idea would be that we'd actually transition some of the fellows to long-term fellowships, maybe year or maybe multi-year, in order to support what's going on. So these are 3 different kind of pathways to figure out what needs to be, what the Institute needs to do and how to support the community in the best possible way.
Okay, thank you. So we just have about 2 or 3 minutes left in this time period. I guess I want to say that from my point of view, I think this last question is really an exciting one, and that there is, I think, some very nice synergies between the different people that have been on this panel, both intellectually as well as in terms of organizations. And I can imagine something that brings everybody together in I think a very effective structure, as well as leading to really good answers to scientific questions. And so my personal hope would be that we can maybe start talking about that in more detail and actually figure out how we could do that. But I also just want to leave the last couple of minutes for anybody else that's on the panel that wants to kind of have any kind of closing statement, closing remarks fairly quickly before we go on to the next talk after this.
So just in terms of logistics, anyone who's really into this idea, that really want to explore some engagement for the next few months, we are going to spend a few hours tomorrow to talk about this. what it means to draft, a plan for engagement, whether we really see our visions converging into an institute. And we will also talk about potential town halls over the next few months. So if you want to participate in this, join us. It will be, just a 2-hour discussion. We can find some good dates for following events. And so we actually take advantage of the momentum that we have with this conference to move forward.
Okay, well then, thanks to all of the panelists. I think this has been, it was a very nice series of, again, complementary talks. And again, I feel like there's a kind of an exciting future that could come out of this. So I think this was very good.